Okay, so last time I started to explain Thevenin and Norton theorems. Okay, and the idea of this theorem is if you have a circuit like this one, for example, if you have a circuit here, I can simplify, and this is the main thing here. I can simplify the circuit by calculating an equivalent circuit. This equivalent circuit, it can have a resistance and a voltage source. This is in case of Thevenin. Or the equivalent circuit can have a current source and one resistance in parallel, as you see here. Okay. So this circuit here is equivalent to this one, equivalent to this one. Okay. So what is the main point here? The main point is this circuit is too simple. So if I want to calculate the current here, if I want to calculate the voltage, it's very easy to calculate here than this one. Same thing here. This circuit, so I can just simplify the circuit by making it this way. Again, what do you mean by equivalent? What equivalent means? It means if you look at the impact on the load or the impact on this part, okay, will be the same. It means the current here is the same current here. Voltage here is the same voltage here. Okay, it's the same thing. That's why I call it equivalent. Okay, and then I told you. So now the question is, how can we calculate these V Thevenin, R Thevenin, Rn, and In? Okay, and the other question is when I have to use this one or when I have to use this one. Okay, which one? Actually, it depends. So if you wanna, in some cases, as you will see later, as you will see sometimes this one is good for me. Sometimes this one is better for me, as you will see in this course. Okay, so any one of them depends on in the situation, as you will see in this course. Okay, so sometimes Thevenin is better, sometimes Norton is better, but in this chapter you need to know how can you calculate both of them. Okay, the good thing is R Thevenin is equal to Rn, RTH equal to Rn. That's a good thing. So now you need to learn how can you calculate VTH, how can you calculate In, and then how can you get this resistance. Okay. And last time I explained it. I told you last time. Let's start with VTH. VTH. So VTH we call it VOC. OC means open circuit. Okay. So here you open the circuit and you calculate the voltage. Which circuit? I want to calculate the equivalent of this circuit here. So I'm gonna open here. What do you mean by open? I'm gonna cut. I'm gonna just cut here. I'm gonna remove this part. Yeah, this part is just one resistance, maybe easy, but maybe in other situation you have a circuit here, whatever the situation is. So you are gonna cut here. I want to calculate Thevenin for this part here. So I'm gonna cut here to make open circuit. Okay. Once I have open circuit here, I want to get the voltage drop between A and B. And this voltage drop is actually VTH. How can you get this voltage drop? Using what I explained so far in this course. You can use Kirchhoff current law, Kirchhoff voltage law, Ohm's law, whatever you have in whatever I explained in this course, you can use to calculate the voltage. Okay. Now this is for VTH. For In, how we can calculate In? It's the same thing, but here again you need to cut here, but you have to put short circuit here. You have to put short circuit after you cut. Okay. And then you need to calculate what current is going to go through the short circuit. And this should be In. So that's why here I'm calling it In is equal to ISC. SC for short circuit. Okay. So again, I'm going to cut. Okay. Then I'm going to put short circuit. And then I'm going to calculate what current here in this short circuit. Okay. How I can calculate it? Using what I taught in this course, Kirchhoff current law, Kirchhoff voltage law, whatever, as you will see in the example. Okay. The last part now, how can we calculate this resistance and this resistance? As I explained last time, I told you there are two ways. There is a general way, which is this one, general way. General way means it can be used, there is no restriction. You can use it in any case. Okay? Here, you just divide VTH by In, as you see here. Just after you calculate VTH, In, you can divide them this way. Okay? There is another way, but the other way here, you have to use it only in case of independent sources. If the circuit contains only independent, so there is no dependent sources. All the sources that are in the circuit are independent, okay? So in this case, what you have to do here, you have to see what is the equivalent resistance here after you cancel the sources. So you have to look here, but you have for sure you have to remove the loop. You have to look here and see what is the equivalent circuit when you look from here after you cancel the sources. What do you mean by cancel the sources? Similar to what I explained in the superposition theorem, cancel the source means any voltage source, you have to replace it by short circuit. Any current source, you have to replace it by open circuit, okay? So that's what I explained last time. And then I give you this example here last time. For sure, I'm not gonna repeat everything. So in this example here, this was an example that has only one voltage source as you see here. And I sent you one email. I told you on Thursday there will be a quiz. The quiz will be, I'm going to give you a circuit that's very close to this circuit. Maybe I'm going to do some changes, but it will be close to this circuit here, to the 5.2. And then I will ask you to calculate the Thevenin and Norton circuit. And then after you calculate the circuit, so after you calculate the circuit, it should look like something like that. Then I will ask you to give me what is the current here, what is the voltage on the load here. So once you calculate the circuit, everything will be very easy, okay? So, but it will be something like that has only one voltage source, but maybe I'm gonna do some changes in the resistors, okay? Or somewhere. But in this example, you need to understand it very well. So anyway, so as I told you here, we opened, as you see here, we opened it here. And after I opened, I need to calculate the voltage here. We call it V open circuit. I did that, okay? Next here, I open here, I put short circuit as I told you, and then I have to find a way to calculate this current here. That's what I did also here. And then in order to calculate the resistors, you have two options. One option you can simply, because I already calculated VThevenin, I divided by IN, and I found it this way. There is another option because I have here only dependent. I don't have any. I don't have any dependent. I have here only independent sources as you see here. So I can simply open. I can open here, and then I see what is the resistance here. What is the resistance if you look this time from here? What is the equivalent resistance after you cancel the sources? We have here only one source. This is a voltage source. So I'm going to cancel it by short circuit. So if I look here, if you look from here, you can find these two resistors are in parallel and they are in series to this resistor. Okay, so you need to get the equivalent resistance when you look from here. Okay, so after I calculated here, I found it is the same thing. I got the same thing, the same result for sure. Okay. Then also last time I explained another case. In this case, we have one dependent here and one independent here. Okay. I explained how can we calculate our Thevenin and how we can calculate the Thevenin and Norton circuits in this case. For sure here, because I have a dependent source here, when you calculate the resistance, I have only one option. You need to calculate V Thevenin or I Norton, divide them, and then you can get R Thevenin. Okay. Anyway, that's what I have here. Again, it's almost the same thing. I opened here. Once I open the circuit here, I need to find VOC this from here, whatever the way you use it. Okay. You read in chapter 4, I explained 3 different ways: nodal, like nodal or mesh, or branch current method. We have 3 methods. Or if there is something easier than that, that's okay. Whatever the way you know, as long as you calculate it correctly, it should be okay. Here, to calculate I Norton, I put here short circuit, as usual we do. But we found something here interesting. I explained it last time. If you have a resistance and then you put a short circuit on this resistance, that means you cancel the resistance. Okay? So if you have any resistance and then you make a short circuit over this resistance, so actually it's like you cancel the resistance. Why? Because all the current here will come here. Nothing will come here. Okay? That's how it is. Usually current is gonna go to the easy path, or the path that has low resistance. That's what you keep in mind. I told you before, if you have two resistors in parallel, and the resistance of one of them is much higher than the other one, it's not a short circuit, but much higher. So we find most of the current will go to the current always like to go through the low resistance in case of parallel. Okay, that's why anyway, so I made short circuit so you cancel this one. Okay? So now the circuit becomes something like that. Now you need to find this one. Okay. More importantly, maybe something also you need to pay attention to here. This one 2ix. Okay, this is the dependent source in 2ix. So ix here in this case is not the same thing ix here in this case because these two completely it's a different circuits. Okay, so here in case of open circuit, you need to calculate whatever ix here. But please don't use the value calculated in ix here. Don't use it here because this is a different circuit. Okay, you understand what I'm saying? So now you consider ix here. You need to calculate ix here. Okay, don't use this value because this is for a different circuit. Okay, anyway. Okay, so now last time I stopped here or I started somehow to explain this one. This is a very special. This is a very special case. Okay, look at this case here. I give you a circuit. This circuit does not have any independent source. It has only dependent source. There is no independent source. You got what I'm saying? So what is the problem if you don't have any independent source? Okay, where energy comes from? Energy comes from the independent source. So if you don't have any independent sources, that means all voltage or current in this special case, everything will be zero. No current. Where the current will come from? Okay, because this one, 3ix, ix has to be zero because there is no dependent sources. Independent sources. Okay. So again, this is a very special case. I don't want to be too confused. In this example, I have dependent source here. Yes, I have one here dependent, but I have another one that is independent. Okay. In this special case, I don't have any independent sources. Okay. So again, it doesn't need any calculation. So that means the voltage is zero, the current is zero. So if you open here, no current will go because again, the current should come from independent. Should come from if there are no independent sources, no current, no voltage. Okay. So anyway, so again, VTH is zero. IN in this very specific case is zero. Is that okay? Makes sense? Okay. Now, again, because this is a very special case. It's different from all the other cases. Okay. So now I will try to use this formula. That's what you told us. We can use this formula here. But if I want to use this formula, I will find it is 0 divided by 0 for sure. It's undefined. So I cannot calculate the resistance this way. Okay. That is why in this very special case, look, I'm repeating the word special case because this again is completely different from the other cases. So in this special case, I will calculate the resistance in a different way. Okay. The way I'm going to calculate the resistance is, I will add here a independent source, voltage source, and the amount of this voltage source is 1 volt. Okay, and then I'm going to say the resistance I'm going to see from here is 1 volt divided by the current Ix. This current here Ix. So again here. Okay, so this is a very special case. I'm going to add here a voltage source, independent voltage source. The value of this source is 1 volt. Then I'm going to divide it by the current drawn from this voltage source. This is one way to do it. There's another way. In another way here, instead of putting here a voltage source, I can put here a current source, and the amount of the current here is 1 ampere. 1 ampere, okay? And again, I'm going to use almost the same formula. The resistance is voltage. So in this case, I want to calculate the voltage here. I use a current, and I want to calculate the voltage. So that the resistance is the voltage divided by the current, okay? So which approach you have to use? Again, try to find which approach is gonna make the calculation easier for you. Okay, so is that which one is easy for you? Okay, is that easy to put a voltage source here? You know the voltage, and then you try to find the current, or it may be easier if you already know the current, but you need to find the voltage. Okay, both of them should give the same results. And here in these two slides, I explained it in. I found the same results. So I'm going to show you how I got the same results. But if you want to sort out, you can use either one of them. Okay? But again, you need to think which one is going to make the calculation easier. Is it easy for me if I put a voltage source and then I have to find the current, or it's easier for me if I put a current source and then I try to find the voltage? Is that okay? Anyway, so let's say here, for example, I'm going to do the first one here. So here I have the voltage here, 1 volt, this way, okay? And then here I need to find Ix. Okay? So, you know, it's very easy here. Ix here should equal I1 plus I2, the Kirchhoff current law. So Kirchhoff current law here, Ix is equal to I1 plus I2. Make sense? Okay? Okay, so now the problem becomes, I need to find I1, I need to find I2. I1 is easy. It's easy to get I1. Why? Because if the voltage here is 0, so here should be 1 volt. Make sense? So 0 here, 1 volt. That means V1 is equal to 1 volt. Very easy, right? Very straightforward. Here, this one is 0. All of this one here is 0. And this one here, voltage 1 volt. So all of this should be 1 volt. That means V1 is 1 volt, very straightforward. So, okay, if you know that V1 is 1 volt, you can easily calculate I1, right? So I1 is the voltage drop, which is 1 volt minus 0 divided by 4, Ohm's law. So if you do this way, you can find I1. Okay, any questions? So what should I find now? I have to find I2, because I need to find Ix. Ix is I1 plus I2, okay? How can we calculate here I2, the current here? Here, I use the Kirchhoff voltage law for, again, look here guys. Such problems, there are different ways to do it, okay? So don't think this is the only way. No, there are different ways. So one way, I did Kirchhoff voltage law for the outer loop. So for outer loop, this loop here, outer loop here, okay? So here, and then to find the I2, okay? This is one way, okay? There is, I can do, so let's see how you can take this loop here as well, okay? I think this can help you as well, okay? You can find this one, and I'm gonna explain if you take the outer loop. I really encourage you, when you go home, if you have different ways, try to use the different ways, okay? Because, and if all of them give you the same result, so you are right, your understanding is correct. If one of them gives you incorrect answer, so something is wrong in your understanding, because I'm saying you applied it in a wrong way. So let's, for example, if I take here the outer loop here, okay? So this one here should be, I'm gonna make the direction this way. Here the current is this way, so it should be negative I2, negative 2 I2, okay? Here you are gonna encounter the positive first, so it's gonna be plus 1. Here you are gonna encounter the negative first. So this one here should be negative 3Ix, this way, okay? And then using this formula here, I can get I2 this way. I2 is function in Ix, okay? I don't know Ix, but actually Ix, you know already, Ix is I1 plus I2. So Ix, which is here, is actually I1 plus I2, okay? You already know I1. I already calculated I1. So Ix is actually, it has one unknown I2. This equation also has one unknown I2. So the only one that's unknown to me now is I2, okay? Or you can do the opposite. You can do this way, and then after you get I2 and you have I1, you can get Ix, or you can do the opposite. You can try to get Ix directly. So I think that's what I did here. Yeah, so here I want to get Ix. Ix equal to I1. Okay, I1, I already found it, okay? I1 is here, I found it. Plus I2, okay? So I2 Here you have Ix equal to I1 minus I2. Okay, so I2 actually equal Ix minus I1. Sorry, or you can get it, sorry, you can get it from this equation here. So Ix here, you can get it from the, I2 here, you can get it from this equation. You can plug in here, and then you can find Ix as the end, okay? Again, I'm going to tell you a very easy way, much easier than what I did also. Again, that's what I'm telling you. Usually such problems, there are different ways to do it. Look how the easy way I will do it. Okay. What is the voltage here? It is 0, right? So what is the voltage here is 1. Okay, so I know V1. V1 is 1. Okay. 1 minus 0 divided by 4 is I1. So I already got I1. I1 is okay. Now let's try to get I2 here. Okay. What is the voltage here is 0. Okay. So what is the voltage here at this point here? What is the voltage? Okay. So it should be 3Ix. Right? The voltage here is 3Ix. Okay. So now what is I2? What is the value of I2 here? I2 actually 1 minus 3Ix divided by 2. Make sense? So now I got I2, I got I1. Okay, I can add them together and they equal to Ix. You have only one known because the voltage drop here is you have only one known, which is Ix. Should I say it again, or it's the same thing like what I did here, but should I say it again? Okay, the voltage here is 0. So what is the voltage here is 1, right? I know the voltage here is 1. Okay, I can get I1 easily. Ohm's law. 1 minus 0 divided by 4 ohm, I got I1. Make sense? Now this point here, the voltage here is 1. The voltage here is actually 3Ix. Because this is 0, so this one should be 3Ix. So what is the current here, I2? I2 should be 1 minus 3Ix divided by 2. This is give you I2, the current here. Okay? So this current here is function in Ix. Okay? And you already know this one. Okay? And Ix here is equal to this one, I1, which I already calculated, plus the current here, okay, which is function in Ix. If you do that, you will get equation like this one, equation only in Ix. You can solve it and then you get Ix. Again, it's almost the same way, but anyway, any questions? Okay, so after doing that, I found the resistance is 10 divided by 3. That means, so this is, okay, that means the Thevenin circuit is actually, we have a voltage source that is 0, and then I have here a resistance that's 10 divided by 3 ohms, okay? By the way, if you have a voltage source that is 0, what it means? It means a short circuit. Why? Because the voltage drop is 0. So the voltage drop between this, from here to here, the voltage drop is 0. Okay? That means it is short circuit. So this one becomes like a short circuit. You understand what I'm saying? So if you have a voltage source and the value is of the battery here, or the voltage source, the value of 0, that means the voltage drop is 0. That means the voltage here is equal to the voltage here. Equal. That means it's equivalent to short circuit. So this is, so now this is Thevenin, this is the equivalent Thevenin circuit. Is that okay? So if I want to make Norton, so again, you have a current source this way, okay? And then you have a resistance here, 10 divided by 3. But again, this is a current source that has 0 current. So no current is coming here. No current. If there is no current, it means open circuit. Very simple. Something that has 0 current is open circuit. Something that voltage drop is 0 is short circuit. Okay? So that's why here, when I find the voltage drop is 0, I replace it by short circuit. That's why when I find here the current flowing here is 0, that means it's open circuit, equivalent to open circuit. So now this is the equivalent Norton circuit. So if you look here, so this very special example is in this very special case, which with no independent sources, Thevenin and Norton equivalent circuit are the same, as you see here, they are the same. Okay. Yeah, sure.
So why is the Vivian voltage 0? Because there are no independent sources.
Yes. When there is no independent, energy is gonna come from independent source. Okay? For dependent sources, the amount of voltage or amount of current, it depends on voltage or current on some other elements. If there is no independent sources, that means there is no current and voltage will come from anywhere because this is a main. Okay. So anyway, so I told you there is another approach. I can calculate the resistance. Instead of putting here a voltage source, I can put a current source this one. And the current source is 1 ampere. All what I need to find the voltage here. Voltage. Okay, this is the second approach. So let's try how we can do it again. So consider this like a problem, and you can use what you learned in this course, Kirchhoff current law, Kirchhoff voltage law, whatever, in order to find the voltage here. I just need the voltage here. Once you find the voltage here, I'm gonna divide it by 1 ampere to get the resistance. Okay. Okay, let's do it. So in this case, look here, guys. V2, the voltage drop here from A to B is equal to V2, right? Because all of this has the same voltage. So the voltage at A is equal to V2. This is 0, right? So now the problem is how can I find V2? That's it. So if I can find V2, I am done. So how can you find V2? Okay. The way you can find V2 is, look here, what is the current here is 1 ampere. So what is Ix? Because the current is gonna come this way. So Ix actually is 1 ampere. So this is 1 ampere and this is also 1 ampere. Okay. So this 1 ampere, that means this is 3 voltage. This one here is 3 voltage. Okay? So I think if you can use, for sure here I'll give you how you can solve it. I'm gonna tell you another, it's almost the same way, but I twist it a little bit, but almost the same way. So look here. So here, if I just use Kirchhoff current law here, I think I can solve it. The current input here, Ix equal to I1 plus I2. Is that okay? I know Ix. Ix is known to me, which is 1 ampere. Okay. I1 is actually V2, which is my unknown. That's what I want to find. V2 divided by 4 ohm. V2 minus 0 divided by 4 ohm. Okay. Plus, what is the current here? It's actually V2 minus V1 divided by 2. Is that okay? What is V1? V1 is 3. Why? Because here is 0 and this one is 3 because Ix is 1. Okay, so if this is 0, so this one should be 3 volts. So V2 minus 3 divided by 2. Now you have equation. In this equation, yeah, here you have equation. It's the same thing I did here. In this equation, you have only one unknown, which is which is V2, VA or V2 is the same. You can just calculate it. I think that's what I did. Look here. So Kirchhoff current law, input here Ix. This one here, which is V2 minus 0 divided by 4. The only unknown I have is V2. That's what I want to find. I want to find V2. The current here is actually V2 minus V1 divided by 2. But V1, you can get it directly for V1 because this is 0, this is 3. Okay? So here V1 is 3. So now we have equation that has only one unknown, which is V2. Once you can find it, divide it by the current, and then you can get the resistance. Any questions? Okay. So now we're gonna have 2 more examples. Okay. Again, I'm gonna repeat it again, guys. This is just a very special case when you don't have any independent sources. Okay. So let's see here. We have 2 more examples here. I'm gonna teach them. So here in this example, you have a current, independent current source, and you have independent voltage source. Okay. I think I'm gonna, in next example, it's also the same thing. I'm gonna repeat it again, but for one example, I'm gonna ask you to find Norton. So still here you have independent current source, independent voltage source. Here, but in this example, I will ask you to find Norton. In this example, I will ask you to find Thevenin. Okay. I want to find the current here flowing through the R. Okay. So here, I'm asking you here, find the current I0, which I here, at different values of R. R equals 6, R equals 10, R equals 20. So for different values of R, you have to find I. Is that okay? To solve this problem, there are two ways. One way, similar to what we did in chapter 4, you can find equations similar to what we did in chapter 4 and solve the equation to get the current. Okay? But this will be the difficult way. Why? Because I need to solve the equation. I need to solve the equation 3 times. Every time here, once you find the equations, I'm plugging R by 6, solve the equation. Then I'm gonna plug in R by 10, solve the equation. Then 20, solve the equation. You got what I'm saying? So this will be the difficult way you do this way. Okay? I think one of the purposes of this example is to learn that sometimes using Thevenin can make the problem easier. You got what I'm saying? So think about it. Which way is better? Is to have 3 equations or number of equations as we did in chapter 3. And then I solve the equation multiple times using different values for R. Is that easier? Or if I can just find the Thevenin equivalent, so now you are going to have very simple equation this way, right? So I can easily replace R here, replace R by 3 values, and then calculate the current easier. Okay? So I think this is the main purpose of this example, to know that sometimes using Thevenin or Norton can make things easier, and that's what we are going to do right now. So now I want to calculate the equivalent Thevenin equivalent here for A and B. Okay, you got what I'm saying? So here I need to find what is the equivalent circuit. So I'm gonna cut here. When I cut, I'm gonna cut here. I'm gonna cut this part here. Okay. So let's do it. So the first thing here, as you see here, guys, I have here. This is the original circuit. So this should be the equivalent circuit. Okay. After I find R Thevenin and V Thevenin. So now I need to find these two. Once I find these two, it will be easy to calculate I0, giving 3 values for R. It will be much easier than chapter 3 using the approaches we explained in chapter 4. Okay, so again, how can we do it? Same thing. It's the same way we always do it. Number 1, you need to open the circuit. So now, yeah, I'm gonna open it this way. And then you have to find the voltage source here. Okay. V open circuit. We call it V open circuit. So we have to remove. I have to remove this part. I have to open here between A and B. I have to open it this way, and then I have to find the voltage drop here. We call it V open circuit. Is that okay? Okay. So let's see how we can do it. Okay. Again, you can think now how can you use what I taught in chapter 4 in order to find the voltage here. Is that okay? Okay. So you can, I'm sure most of you, if I give you this problem to solve it, I'm quite sure most of you are gonna overcomplicate it, and they make branches, they make loops, they make it with 3 equations to solve it. But usually, sometimes if you have a good observation, you can solve it quick. Okay? I'm gonna tell you what I mean by quick observation. The observation here, what is this current here? Again, you understand what I'm saying? So you can use what I taught in chapter 4, either the mesh, the nodal method, branch method, current branch method. You can use any one of them, make equation, solve the equation. But as I told you, there is one observation here. Okay, if you notice this observation, I'm gonna make it easily now. Okay, so look here. This current will come here, okay? Where this current is gonna go? This current is gonna split, right? Between these 2 branches, this way and this way, right? So the current, this is 2 milliampere. This 2 milliampere will come here, and then some of them will go this way, some of them are gonna go this way, okay? And they are gonna come again, so whatever current will come here, and the current come here, they will be added again and come here. Makes sense? So the good observations that can make everything easier is I already know the current here, which is 2 milliampere. You got it? This is very important observation because this can make the solution very straight, very easy. Again, the current here is going to split. Some of them will come here, some of them will come here, but they will be added again, then it will come. So the current, I already know, the current here is given to me, it's 2 milliampere. Okay? So I know the resistance, I know the current, I know the voltage drop here, but I don't know what is the voltage here. It's only one unknown. So if I just apply Kirchhoff voltage law here, I have only one unknown. I can easily calculate VOC using just one equation. You got what I'm saying? So, and that's what I did. So what I did here, I'm going to apply Kirchhoff voltage law here. Okay. When I apply it, you can see here, this is negative 12. Yeah, negative 12 is here. Then it's going to be voltage drop here, VOC. This is the unknown. I don't know it. Okay. And also here, and then here, because I know this current is 2 milliampere, so this should be negative 2 milliampere times 4. Just very one quick equation, and then you can get VOC quickly by 20 volts. Is that okay? When you go home, guys, you can practice. You can try another approaches, okay? And try to see if you are going to get the same result. Very important, okay? Very important when you go home. Try another way. You can see if you can take a loop here, take a loop here, whatever, okay? Whatever the way you can do, okay? For sure, if I take this, why you took this loop here? Why you didn't take this loop? You need to ask yourself this question. Okay, guys, I'm going to say it again. Because I'm giving you the easy way how I solved it, okay? You'll understand it, but you need also to ask yourself, okay, so why you did this way? Why you did not take this loop here? Why you did not take this loop, whatever, okay? And maybe you are right, but let's think about it. So if I take this loop here, okay, I will have another unknown here, okay? So I will have the current here is unknown, right? So anyway, I will leave it to you. It may be easy case as well. I have no idea. Or you can take this loop here, okay? You can think about it. It may be an easy case, okay? Because if I take here, if I take this one here as well, I can find. So here I'm gonna have two unknowns. That's a problem. So I will have I here, and I'm gonna have I1 here. So I will have two unknowns. Okay. That's why maybe I need to take another loop, whatever. So the equation will have two unknowns. Anyway, I want to think about it. So I just took the easy case, okay, based on the good observation here. But when you go home, try another approaches. Okay. Anyway, so I already found VOC. So what's else I have to find? Okay, I need to find the resistance. Okay, to find the resistance, I can do it in one of two ways. Okay, guys. The first way, as I told you before, here I'm not asking you to do Norton. Listen to me. I'm not asking you to do Norton. That's why it's not required to calculate I Norton. It's not required to calculate it. Okay. If I ask you to calculate I Norton, it would be, so there is no way you have to calculate I Norton, and then once you have V Thevenin and I Norton, you can get the resistance. Okay. But now, because I just need Thevenin, so you don't need to calculate I Norton. Okay. So now I have two options. Okay. One option, I make a short circuit here, and then I need to find I Norton. Okay, and then divide V Thevenin by I Norton to get the resistance. This is one case. If this is easy for you, okay, go ahead. This is okay. It should be okay. The other case is, okay, wait a second. I can, as I told you before, I can just look here. I can look here. I can remove these sources by making this one short circuit and making this one open circuit, and then I will look from here, see what is the equivalent resistance. Yeah, this is the second approach. Whatever you think is easier. I'm going to use the second approach because if you make short circuit here, you may need to find equation and it may be more difficult. But if I just find the equivalent resistance from here, it will be much easier. Okay. So again, you can do like a practice when you go home. You take short circuit like a practice and see how can you find it. Okay. So what I'm gonna do right now, as you see here, guys, I'm gonna remove the two sources. So this one is a photo source. I'm gonna replace it by short circuit current source, I'm gonna replace it by open circuit, and then I wanna find what resistance when you look from here. What do you mean by look from here? Can you clarify? Look what I'm saying, guys. It means if I connect a source here, what resistance? Okay, let me take this one here to work. Okay, I want to write. So let me take this one. Where is okay. So look, you guys, what I'm saying here, I wanna find the equivalent resistance from here. So what this means? Because usually if it is something like when I explained before, maybe it was easier. So before, you remember when I explained something like that, I told you I'm gonna look from here. So when I look from here, I will find this one here is series with this one. So what it means when I tell you I wanna find the resistance, it means if I connect a battery here or a voltage source, okay? So how you will see the circuit? That's the meaning of it. So if I connect the source this way, the current will come here. The current is going to split this way. So I will see in this case, I will see that this resistance is in series with these two resistors, which are in parallel. You got what I'm saying, or this is difficult? You got what I'm saying? I'm going to do the same thing now. So here. Again, guys, I'm not sure if this is difficult or not. But again, in one example, we had a circuit like this one. I told you I want to calculate the equivalent circuit when I look this way. Okay. So what this means? It means if you connect a source this way, a battery, a voltage source, whatever it is. Okay. So what resistance this battery will see? Okay. The way you have to think about it, so you will give current this way, and then this current is split between these two. Okay. So that means this one should be a resistance. I'm going to call it R1. And then here we have another resistance. I'm going to call it R2 parallel to R3. Then it's the same current here flowing in R1. It's the same current flowing in these two resistors. Okay. So that, and then I'm going to say the equivalent resistance is R1 plus, because they are in series, R2 in parallel with R3. You got what I'm saying? Now I want to do the same thing right now. So here, I want to see what is the resistance you can see when you look from here. Okay, so what it means? It means, by the way, it looks complicated, but when I do it, it will be very trivial. You will see right now. It means if I connect the battery this way, what resistance this battery will see? Let's think about it. Okay, you find it's very easy. So the current will come here, and then the current will come here, and then come here. Is that okay? And some current can come here and then go back to here. Is that right? Is that right? Usually for any circuit, the current has to get out from here and then come back to here. Because I'm saying you have to close back from positive to negative. So get out from the positive, it's going to go somewhere and then it has to come back, right? But this is not the case here, right? So this one is okay. So when the current here is going to come here and then it's going to come this way. Okay, so this one is okay. This is a base. What about this one here? Okay, so this current will come here and then come here. Then will come here. Okay, or will come here. This is a short circuit, right? So will come here. So actually what happens here, these two resistors are not going to make a base between the positive to the negative. Okay. So actually here, so all the current will just come here. Okay, nothing will come here because when the current comes here, there is no base. There is no base it can take because this one is open circuit here, so it cannot even come this way. Okay, so there is no base for this current to come this way, okay? There is no path to come here, okay? And even if you think, if you have a battery here, okay? And if the current, for sure, we agree on this one. We don't have any problem with this one, okay? But do you think some current can come here and then come here, will come here this way, this path this way? I don't think so. So this one is, what I'm gonna do right now, I'm gonna like redraw it to make it easy. So I will draw it. So it's like you have a battery this way, and then you have here resistance this way, which is 4 kilo ohm this way, which is this resistance. And then also I'm gonna redraw it. So here from this one here, you have a resistance here, which is 2 kilo ohm. And then you have another resistance. So here I'm going to call this one point A and point B. Okay? And then you have another resistance, which is 2 kilo ohm. Okay? And then this resistance is connected to point A. Is that right? It's the same thing here. So you have point A and point B. So number one, I have here one path from here, A to B this way. Okay, so here this resistance is connected here between A and B. Okay. Also, you can see here from A, we have a resistance connected to C. So here I'm going to put this one C. This point I'm going to put C point. Okay. And then from C, it's going to go back to A again. Okay. So it's going to be something like that. So in this case, there is only one path for this current. It's going to be this way. And say the resistance you will see is only 4 kilo ohm. Yeah, so that's what I'm explaining here. Yeah, so what I'm explaining here, same thing like what I explained, we just redraw it. So I can see here, if you put a battery this way, okay, so all the current will come this way. So the current is not gonna come here and then come here and go to the positive again. It's not gonna do this way, okay? The current has to flow from the positive to the negative. So anyway, so if you can see here, the resistance actually is 4 kilo ampere. So now I find the resistance, and already I find the voltage here. So it's now I already have everything I need to calculate the Thevenin. So you can see here, this is the circuit now I have. The voltage source is, or V Thevenin, is 20 volt. The resistance here is 4 k ampere. Now this is the interesting part here in this problem. So what is the current here? The current here is 20 divided by 4 plus R, right? Yeah, here. The current here is just 20 divided by 4 plus R. Now, because I give you 3 values for R, you can easily calculate the current. Just remove this R, put the value. Remove R, put the value. Remove R, put the value. Okay? That's why Thevenin now makes this problem much easier than using any of the techniques I explained in chapter 4. Any questions? Okay. So here, the last example I have here is almost the same thing. You have here voltage source, you have current source, but this time I'm asking you to calculate Norton circuit. Okay. So you know in Norton, number one, you have to remove this resistor. You have to remove this resistor. Okay, you have to, and then you have to put short circuit here, and you need to find the current in the short circuit. Okay, and that's what I did here. So here, I need to remove this one. I put short circuit here, and then I need to find the current here. This current is I short circuit. Is that okay? So how can you find the current here? Okay, so you need to use any approach I explained in chapter 4 to calculate the current here. Okay. So here, what I did here is I can for this one here, I can calculate Kirchhoff voltage law for this equation here, this one here, and you can see what is the voltage here is 0, right? So voltage here is 0. The voltage here also is 0. So 0 and 0. Is that okay? 0 and 0. Okay, can you calculate the current here? Yeah, this is 0, this is 6. This is 0, this is 6. So the current here is actually 6 minus 0 divided by 6. Okay. Again, how I made it? The voltage here is 0. This is a short circuit. So this one also should be 0. This is 0. And this is 6 volts. So this should be 6 volts. 6 volts and 0. So it should be 6 minus 0 divided by 6. Okay. So what I explained right now, you can put it in an equation. Like what I did right now in just a very easy, quick way, it's the same thing you are going to get if you apply Kirchhoff voltage law here. Okay. So if you apply Kirchhoff voltage law here, so you will get up. By this way, you can get I1. So I can get the current here I1 easily. Okay. I need to calculate the current here. The current here, we have here I1. Here we have this current is gonna split between this current and this current. Okay, so now I need to find the current here. I need to find the current here on this resistance, right? Because if I already know this current, I need to calculate this current. So using Kirchhoff current law, I need to find the current here. Make sense? So we need to find the way. I need to find the way to calculate the current here on this resistance. Is that okay? So here, so I'm gonna. So here, what I did. So here, that's what I'm telling you. The current here is actually I1. I already calculated I1 minus I2. So I need to find the current here, which is I2. Okay. Again, you can think in different ways. Okay. And here I applied Kirchhoff voltage law. Is what we know, but there is there may be a very easy way to do it. Okay, other than what I explained here. No, here nothing is new. I just applied Kirchhoff voltage law and Kirchhoff current law. But let's think about it. I will try to find another way. So look here, guys. I want to find the current here. Okay, so you have current here, and you have current here. Okay, and then you have current here. Okay, so I already know this current. So if I take Kirchhoff current law here, then I need to find that's what I need here. I need only to find the current here because I found this. I already know this current here. Okay, so let's take it in. I'm gonna take it in Word. So look here, guys. What is the current here? The current here is 0. So what is the voltage here? It is 6 volt. Very easy. This is short circuit. So the voltage here is 0 volt. Okay, that's easy. So what is the current here? Ohm's law, 6 minus 0 divided by 6, which is 1 ampere. So, okay. So now, that's what I need. I need to find the current here, okay? To find the current here, you need Kirchhoff. You need to find here, I'm gonna call it, for example, I2. So all what I need to find I2, and then once you find I2, I can apply Kirchhoff current law here. So I have this one here, this current enter, this current here leaving, this one also leaving. So I can add it. So here, so now the problem, I need to find I2. Once I find I2, okay, so I can find this one easily. Makes sense? Okay, let me finish this one, then take your question. Okay, so for example, so what I'm gonna do right now is, look here, I'm gonna call it, for example, this one is VA, and this one is 0, okay? Then we have a current here, I'm gonna call it I3. Then I will apply Kirchhoff current law here, Kirchhoff current law. So here, you have one is input, which I2 should equal to, I2 plus 2 milliampere. So this one is entering. This one also is entering, should equal to I3. Is that okay? So here, if you look at what is I3, should be VA minus 0 divided by 3. So this one is actually VA minus 0 divided by 3 kilo ohm. Okay, what is I2? I2 actually is 0 minus VA divided by 3 kilo ohm. So now I have equation, and this equation have only one unknown, which is VA. After I calculate VA, I'm done. Once I find VA, so I can easily calculate I2, which is 0 minus VA, okay, I2. And once I have I2, and once I have I1 and I2, I can easily calculate this one I short circuit. Okay. Yes. What's your question?
1 amp is going across the 6
Yeah.
ohms. Why wouldn't they all go down straight from through AB because it's a short circuit?
Yeah, but because this is a very good question. So why? So here, why this current is gonna just come here this way, okay? And nothing will be divided here because you have another source here. So this source will also give some current this way. So if you have something like that, and then I have resistance this way, and then I have, if this is the situation, I would agree with you. So all the current will come here, and everything will come back to here. Nothing will go here because I put here a short circuit between these two resistors. So I'm gonna cancel. This is a very good question. I can cancel these two, and everything will come here. But in this case, because you have here, you have also current coming this way, okay? So you have here current coming this way. So that's why, because if you have a source here, this source also will give some current this way. You got what I'm saying? So let's see what current what was the value of I short circuit we have here. We calculated. I short circuit, it was 2 milliampere. This one here was 2 milliampere, right? After I did the calculation. That means, yeah, I think my answer is that we have 6 ampere here because of the impact of, that's my answer, because of the impact of the source. If I don't have this source here, I would say this is a short circuit in 2 resistors. And in this case, yes, this short circuit is going to cancel the resistor, everything will come to here. You got what I'm saying? But here it's a different case because you have a current source. That's my answer. Okay. So now I found, so now I can make Norton this way. I can make Norton this way. We found I, we found R. Then we need to find the current here. You can calculate the current here. You remember current division theory. That's an easy way to do it. Current division theory, which is the current here. This current here, which I0, I know equal to the total current 2 milliampere times this resistance divided by the 2 resistors. Current voltage low. Okay. So here, yeah, here. So I know the current here in this branch equal to the total current, which is 2 milliampere, times the other resistance divided by the summation. Once you have this formula, it's going to be very easy. All what you have to do is you just replace R by one value, then you can find I0. Then you can replace R with some value, you can get I0. You got what I'm saying? So I don't need to repeat the calculation. It's going to be too easy. For different values of R, I can calculate I0. Any questions? Okay. So I finished Thevenin and Norton. We will use it in this course in several places. Because sometimes it makes the calculation easier, as you will see in this course. So as I told you, I'm going to give you on Thursday, I will give you a circuit like this one, and then I will ask you to give me Thevenin and Norton equivalent. Okay. Now I'm going to move to another topic here, which you call it source transformation. So let me go back to the beginning. So I told you in this chapter, I'm going to teach number 1, superposition theorem. That's what I did last time, superposition. Okay, you remember it? If you have multiple sources, I can just put one source, cancel the other sources. Then I calculate the current or the voltage, okay, because of this source. Then I have to repeat it for the other sources, and then I have to add everything together, okay? That's what superposition theorem. Then here, Thevenin and Norton, I already explained them. So in this chapter, we have two more theorems. They are very easy theorem. One here is about source transformation, the other about maximum power transfer, okay? They are very easy, much easier than what I have explained, okay? So let's go to the next one here. source transformation. So we have proved this one using Thevenin and Norton. We have proved that if you have a circuit like this one here, this circuit using Thevenin is equivalent to this one here, using Thevenin. Also, this circuit is actually equivalent to this one here, a current source and a resistor in parallel. This one, a voltage source and resistor in series. We have already proved that, okay? So this circuit is equivalent to this one, and also this circuit is equivalent to this one. Also this circuit here using Thevenin is equivalent to this circuit that has Norton, okay? So all of them are equivalent. You understand what I'm saying? So now what I'm gonna do right now is I'm gonna say, okay, so that means if I have a circuit like this one here, should be equivalent to this one here. That means if I have a source and the resistance this way, I can change this circuit to this circuit. Okay? So again, let me put this way, guys. When I explained Thevenin, I told you I want to move from here, from this circuit to this circuit. When I explained to Norton, I told you I want to move from this circuit to this circuit. Now, because I'm explaining something we call it source transformation, yeah, okay, so this one here is equivalent to this one. That means, in general, if I have a voltage source, it doesn't need to be coming from Thevenin. If I have a voltage source, okay, connected to a resistance, so this should be equivalent to a current source to connected to resistance. It doesn't need to be Norton or Thevenin. You got what I'm saying? That means if I have a voltage source, I can make a current source. Or if you have a current source, you can make it a voltage source. What do you mean? I'm getting what I mean. I have a circuit. The circuit has a voltage source. Okay? Maybe it's easier in the calculation if I can remove this current source and replace it by a current equivalent current source. This makes the calculation easier. Or the opposite. Maybe the circuit I have has a current source. But if I know a way to convert this current source to a voltage source, equivalent voltage source, so this may make the calculation easier. Yes. Okay? That's exactly what we're doing right now. So what we're gonna do right now, forget Thevenin or Norton. Forget. Okay? So I just use Thevenin and Norton just to prove to you that if you have a voltage source connected to resistance, I can transform it to an equivalent current source and the resistor, or the opposite. How? I'm going to tell you how. You understand what I'm saying? It doesn't need that this voltage source is coming from Thevenin. It doesn't need that this current source here is coming from. No, this is now general. But how I can do that? I'm going to tell you how, and this is very easy, very trivial. Okay, so in general, guys, if I have a resistance connected to voltage source, I can transform it to current and current source and resistance. How? I'm going to tell you how. This is the relation. Number one, this resistance equal to this resistance. This is the first easy part. Number two, the current here, this current equal V divided by R. Or V equal I times R. You got what I'm saying? So again, it doesn't need to be Thevenin or Norton. Now I'm talking about, I'm just leveraging, I'm just using Thevenin and Norton to have a new theorem. The new theorem is, if you have a voltage source this way connected to resistor, I can make it this way. How? Number one, this resistance equal to this resistance. Very easy. Number two, this current source is actually equal to V divided by R. Very tricky. Okay? So this one is equivalent to this one. So if you have a circuit that has this source this way, I can replace it with this source and then I can do the calculation. For sure, I will do that if this can make the calculation easier. But if this will make the calculation more difficult, I would not do it. That's for sure. I can also do the opposite. So if you have this one, okay, how can you get this one? Very easy. This resistance equal to this resistance. Okay. The voltage here is I times R. That's easy. Okay. Let's see example to understand how. So again, what this theorem is telling me if you have a circuit, this circuit has a voltage source. If you think it's easier for you to replace the voltage source by a current source, you can do that. Also, you can do the opposite if you think this is easier for you. So if you have a voltage source, you can replace it by a current source. If this by a voltage source, if this can be easy for you. So let's. I think I have a couple, 1 or 2 examples. Yeah, I have 2 examples here. So let's see this example. Look here, guys. Okay, I wanna find the voltage here. Okay. Okay, you can apply what we learned in this course. You can make equation, you can solve the equation, chapter 4. You can use what we have done in this course. Okay, you can solve it this way. So I can solve this problem by finding the voltage here. You can make equation, you can solve the equation similar to what we do. But now, okay, now I'm gonna make a trick. Okay, because of this trick, the problem will be very easy, very simple, as you will see right now. Okay, let's see how I will make it. Okay, okay. So I can replace. So now here I have a current source with resistance. For sure, I'm gonna add these 2 resistors together. So this is what this theorem is telling me. If you have a current source and then a parallel resistance, I can make it voltage source. So look here, look at the point. The point here is that, look here, guys. I have here a voltage source and have a current source. The point is, if I can replace this one by a current source, if now I have 2 current sources. Sorry, if I can replace this one by a voltage source, so now I have voltage source and voltage source. I can add them together or subtract them together based on the polarity, you know what I'm saying? And the circuit will be too simple. So now, this is the way I think about it. If I can replace this current source by a voltage source, circuit will be very, very simple. Okay? So now I will start from here. Okay. So, but here you have 2 resistors. Okay, I can mix them 1 resistance 3 kilo ohm in parallel. Okay. So so here, look what I did. I didn't do anything. I just added these 2 resistors together. Okay. So I just redrew the circuit. So this circuit is similar to this circuit. Nothing is new. I just added this resistance, and then I just moved them to here. Nothing is new. I didn't change anything. Okay. Now I can simply replace this one, which is current source. I can replace it by a voltage source this way. Okay, how can you make this change? Okay, what is the resistance? This resistance equal to this resistance. Very trivial, very easy. The amount of the voltage here equal I times R, 2 times 3, which is 6 volt. Very easy. You got it? Did you see what I did? So number 1, I want to replace the current source by a voltage source this way. Okay. To do that, resistance here is the same resistance like this one. Voltage here is actually I times R. Very easy. Okay. So now this is my circuit. Okay. So now the circuit becomes very easy. All what I have to do now, you have 2 sources. These sources are in series, and positive is connected to negative. Positive to negative. So if you remember, I explained it before. In this case, I can replace it by only 1 source. This source is, you can add them together. So let me explain it here. So if you have for example, this is positive, this is negative. And then here, this is positive, negative, this way. Okay? This is 3 volts, this is 4 volts, for example. So in this case, negative is connected to positive. Okay, so I can replace this one with only 1 source, positive, negative, and this one should be 7 volts. Okay. Similar, when you have 2 batteries, 1.5 volt, you connect them in series, you are gonna get a source that is 3 volts. Okay, it's the same thing here. But what if the polarity is different? For example, this one positive, negative, but this one also positive, negative, positive. Okay, so in this case, you have to subtract. So in this case, you are going to have only 1 source. I'm going to take the big one here. So negative, positive, and this one should be 4 minus 3 equal 1 volt. You have to subtract. Okay. Yes.
So does the resistor between them have in this case?
This is a very good question, very good question. Because in this example, I have a source here, and then I have a resistant, and then I have a source here. This is the part that's confusing you, right? It's a very good question. Actually, they are in series. They are in series. So if you switch, it's not going to make any difference because they are in series. It's a very good question. I know things like that confuse students, okay? So if you have, guys, in general, anything that's in series, if you have R1, R2, and then R3, it's exactly the same thing. If I just switch R3 here and R1 and R2, you can say same thing for sources and so on. So yes, this is a very good question. So what happened here? Yeah, we have resistance in the middle here. Because they are in series, I can just move this one here. Okay. So now, if you look what I did here. For sure, the solution here will be much easier than if you are use the original circuit to calculate the voltage. Okay, so here it will be very, very quick. So now, how can you get the voltage here? I can apply voltage division, which is 9 times 6 divided by 6 over 3. Voltage division here. 9 times 6 divided by 6 over 3. Okay. So now I made it easier. That's what I'm saying here. So what I'm saying, guys, is that if you have a voltage source, if it is easier for you, you can convert it to current source. Okay, this can simplify the sum. Also, you can do the opposite, and I think that's what I will do in the next example. So that I got this example from the textbook. So this example here, you have here a voltage source. I want to get the current here. So I found if I can replace this voltage source by a current source, my problem would be much easier. Okay. So here, and that's what I did. So here I'm gonna replace this one by a current source here, as you see here. How you did it? This resistance will be the same resistance here. What is the current? The current actually is V divided by R. Okay. I think this is wrong. Okay, this should be 12 minus 2. Sorry, 12 divided by 2. Okay, because in the original book this was 4, something like that. But anyway, so here this is wrong. This shouldn't be 3. This has to be, maybe I'm gonna correct it. I think I'm not sure if this is corrected in the calculations. But anyway, so I will see it. Anyway, so here this is 2K, but the source here, the current source here should be 12 divided by 2, which should be 6, not 3. Okay. Anyway, then after that, I can merge these two together. Okay, because again here, because they are in parallel, I can merge these two together by making it. This is 3 down. This is 2 up. Should be 1 down. Okay. Now, if you have a circuit like this one, the circuit would be much easier here. You can say 1 mil. You can see the current here is equal to the total multiplied by 2 kilo ohms divided by the summation. So it would be much easier. I want to tell you something quickly about the direction of this current. Why you make it down? Why it's not up? Because if you look here how the resistance is made, because the current will go. If you look at the resistance here, the current will be down. Okay, this is very important thing. So look at the direction here, guys. Here the current will go this way. From this source, the current will be this way. That's why I'm gonna make it down. Okay. So this is the first thing I made. This current has to be down. Okay. So here and the second thing I made, I can merge these two current sources together, and because they are in different directions, this one is down, this one is up. So I'm gonna subtract. So the one we have here is 3 minus 2. For sure, that's not 3 unless you can make this one 3, but you have to make this one 6 volt. I will correct it. So I will make also this one 6 volt, so that this will be 3. So here, 3 minus 2 is 1 in this direction. Once you make this way, okay, so now the circuit became too easy. Okay, guys, so let me finish the conclusion to finish today's lecture. If you have a voltage source and you think it's going to make the analysis of the circuit easier if you can convert it to a current source, yes, you can do that, okay, as I explained, so that you can add sources together. This makes the circuit easier, okay. Same thing, if you have a current source, you can make it go to source issue, okay? We finished the quiz 2, so become, so you are going to quiz 2, okay?